we looked at the effects of mismatch class on a differential amplifier, right? We just looked at the input referred offset voltage, okay, and we found that it had some dependence on the VT mismatch, the RD mismatch, and the W over L mismatch, and it has some, that is the dependence, but then it's also sensitive to the VGS minus VT. So if you want to minimize the input referred offset, you have to minimize the VGS minus VT, right? Okay. Now, actually, before we go there, right, I wanted to point out one thing, I think, which may not have been clear last class, which was it from, yeah. So this is your resistor distribution, right? So it has some kind of Gaussian distribution. So that is actually the distribution of the value of the resistor, right? And that has, right, what happens is depending on several things, it could be related to W over L, the width and length of the resistor, it could be something related to the process. There are several things which give rise to this kind of distribution, right? So, and there is also a second level of, so this is your random change in the resistor value, right? So there are other effects which may be systematic, which may or may not be included, right? So if you look at it from an overall process point of view, the overall, depending on certain process parameters, right, over time or between different wafers, you could have changes in doping levels, you could have changes in other things, which can also affect the resistance value or the capacitance value or anything. Okay, so you have to make a clear distinction between systematic cases and random cases. Okay, just wanted to point that out in case that was not clear. So the overall variation in the resistor value could be, so if you see this, it says this sheet resistance varies by 100 plus or minus 30%. That if you put it this way, it usually refers to the overall, you know, if you get a process, if you're trying to hit 100 ohms, you could get anywhere between 70 ohms and 130 ohms. That's what it means, right? It does not specifically refer to the mismatch. That's what I'm trying to say. Okay, that refers to the overall distribution of the resistance itself. Okay, so the mismatch itself has certain, if you remember, we talked about A delta R by R, right? We talked about parameters which we talked about, for example, AVT, AR, AC, and so on. Those represent the random components, right? The random mismatch components. Okay. Okay, so we looked at the, okay, so coming back to your differential amplifier. So we looked at, you know, there is some certain mismatch, there is some distribution for the, you know, which causes the input referred offset. Okay. Now suppose you want to analyze this differential amplifier. Now we want to try to bring it to the old form which we recognize, which is your differential half circuit and common mode half circuit, right? So let's try to quickly, what I'll do is I won't do it for the full differential amplifier. So it's a little bit involved, you can do it by yourself, it's not that difficult. I'll just show you how to do it for a resistor. For example, if you have mismatch between two resistors, how you would separate it into a differential and common mode half circuit. Okay, then you can try it out by yourself and see what happens to your other parameters of your differential amplifier. So let's take the case of two resistors, R1 and R2. I'm going to call the currents I1 and I2, the voltages V1 and V2. Okay. So now between these two resistors, you can define a differential quantity, which is, let's say the differential current would be I1 minus I2, right? The common mode current I1 plus I2 over 2. It's similar to the analysis we did last time, right? Use that, right? We're going to call delta R is the difference between the resistances and R is the mean value. Okay. Now you are interested in the differential voltage and the common mode voltage. What is VD? Is V1 minus V2. I1 R1 minus I2 R2. Similarly, VC is I1 R1 plus I2 R2 over 2. Okay. Now what you can do is, you can put in expressions for I1 R1 inside this and find out VD as a function of ID, right? And because now that you are separated it this way, ID is I1 minus I2 and IC is I1 plus I2 by 2. You can say ID is IC plus some delta, ID over 2, and then, you can do it, try to separate the differential and common mode components. So let's do that for VD. That's I1 R1 minus I2 R2. So I1 is IC plus ID over 2. R1 is R plus delta R over 2 minus I2 R2, which is IC minus ID over 2 times R minus delta R over 2. You can expand this, neglect the, the second order terms, and you can show that this is approximately ID times R plus IC times delta R. So in other words, if you're, if you had no mismatches, delta R is 0, then you would go back to your old case, which is VD is ID times RD. Similarly, you can show that VC is IC times R, that is your ideal quantity, plus ID times delta R by 4. Okay? Okay. So now that we have, so what this means is, earlier in the ideal case, VD depended only on ID and VC depended only on IC. Now you have dependencies on, cross dependencies, right? So now what do you do? So you take your old half circuit. So this one can be represented just by an old half circuit, which is just R and R in this case, right? But now you need to add in this case, for the differential voltage, you need to add an extra extra voltage source of value IC times delta R. So let's take the differential half circuit. So you'd have R. I'm going to call this current ID over 2. VD over 2. What is this? IC times delta R over 2. Okay? This would be the differential mode circuit, half circuit. The common mode half circuit will have, it will be very similar. This is overall voltage is VC, resistance is R, current is IC, and now this one is ID over 2 times delta R over 2. Okay? And so yeah, so this is a differential half circuit. So what you see is, you see some cross dependencies. ID depends on IC and IC depends on ID, which is as expected. Okay. Now this makes it easy, right? Now, for example, if you have mismatch in the current, in the transistors, what is the transistor equivalent circuit? It's a GM, right? Now you can say you have a GM, it's just like, it's a transconductance, right? So you can say it's GM times V1, you have a current I1, you take two sources. Now you'll get cross dependencies, right? You'll get a delta GM times the other voltage. For example, current in one branch will not depend only on the input voltage, but the voltage on the other branch also. Okay? And what this means is, you are used to defining an overall common mode gain and a differential mode gain. You have heard of these two terms, right? Common mode gain and differential mode gain. So you normally you get these two. Common mode is VOC by VIC and differential mode gain ADM is VOD by VID. But then you also have these two terms. Okay. What is this? VOD by VIC. VOC by VID. So in other words, yeah, so these will also be, if you can define these kind of terms, they'll also be give you some idea of the mismatches inside the circuit. Okay. Okay. So suppose now we have done it for a differential pair. Let's also do it for a current source, because if you remember, we are trying to create a parallel. The reason we want to do that is we are trying to create a parallel between noise and mismatch. Okay. If you see, there are actually lots of parallels, but let's just do the mismatch analysis for a current source, and then we'll come back and see what the parallels are. Okay. So this is your mirror branch. Okay. So I'm just going to write, we'll assume they're in saturation, so I'm just going to write it as VGS minus VT the whole squared. What is delta ID now? So you have a dependence on W over L. So it's dou ID by dou W over L times delta W over L. Okay. Plus dou ID by dou of VGS minus VT times delta of VGS minus VT. Okay, this will give you the current mismatch between the two branches. What is this? Did I made a mistake now? Yeah. Okay. Right? Plus there's a delta VT here. And now that you have said delta VT, it should be a minus. Right? So now what you are interested in is delta ID over ID. This will become delta of W over L over W over L minus okay minus 2 delta VT over VGS minus VT. Right? What does this mean? If you want to minimize the mismatch between the two output currents, you now need to maximize VGS minus VT. Okay? Unlike the differential amplifier case, here you are interested in the overall output mismatch. Okay, so you need to maximize VGS minus VT. And of course, this comes with the same problems as before, right? Now you have to worry about headroom and so on, right? Same thing with noise. And if you see, this is actually a very close parallel with what we noticed for noise, right? If you remember, for a differential amplifier to minimize noise, because the input referred noise was inversely proportional to GM, correct? You wanted to minimize input referred noise. Okay, so you wanted to minimize VGS minus VT for the differential pair and maximize VGS minus VT for the current source, right? For noise. Turns out, for mismatch, it is very similar. Okay, the behavior with VGS minus VT is very similar. That's the idea. Okay. Okay, so now we know that all physical circuits have offsets because you can't get rid of mismatch. This is a random quantity. Okay, you can design in some sense for it using VGS minus VT, but you're always going to have it. Can you do anything to completely get rid of it, right? So what we'll do is, in the time left in today's class, we'll try to go through some of the techniques you can use. Okay, this will go at a somewhat high level. Okay, so let's start off with the first one. First of all, why not just increase VGS minus VT? Obvious thing is headroom, right? What else? Let us take a differential amplifier. You want to reduce VGS minus VT. Okay? What does reducing VGS minus VT mean? For a given current, it means larger devices, right? Larger devices means lower speeds, higher power, and so on. Okay, now because you have larger capacitance, you may need higher power to drive it. So in general, you go down a path where you're forced to increase power and area and several other things. Okay, so that's why you want to find out techniques to cancel offsets. So let's take so we want to cancel offset in this amplifier. Let's say this gain is AV, and I'm going to put two series capacitors, C1 and C2. Okay. And I'm also going to add two switches, S1 and S2. Let's call these nodes A and B, X and Y. Okay. So we're going to find out. So obviously normal operation is when S1 and S2 are open. So this is your input port. Okay. And that's your output port. So obviously normal operation is when S1 and S2 are open. Right? Let's try to find out what happens when S1 and S2 are closed. Okay. In other words, the switches are on. What is V out when the switches are on? So I'm going to call this as V out, so to avoid confusion, okay? Because that was the original output of the amplifier. What is V out? It's not 0. Why is it 0? S1 is 0, S2 is shorted. What is V out? It's not 0, right? So it's AV times VOS, correct? Okay? So this thing actually is quite interesting because okay, so now let's say you open the switches, right, during normal operation. So what you have done is you have brought the overall system to a state where from these two ports AB to XY, when input is shorted, output voltage will also be 0. You have brought it to that state because what happens is this voltage AV times V out, AV times VOS is actually stored on these capacitors, this offset voltage. Okay, so now what happens is when you open this overall system between AB and XY will respond to only differential voltages delta VAB and delta VXY instead of responding to the offset, right? So, okay, so you've basically made, when VAB is 0, you've made VXY to be 0. So overall, between AB and XY ports, it looks like an amplifier with no offsets, right? So in practice, what you'll have to do is, so you'll have to, obviously now you want to apply, so what all do you need to do? You need to apply input, so you need to make sure your input is isolated from your AB nodes. That's one thing you need to take care of, right? In this case, you can't directly apply input because if you turn off switch S1, then you're basically shorting V in. So you need a set of switches to isolate V in first of all. Okay. Next thing you need to do is you also need to establish common mode voltages at the input and output. So in general, you'll need more number of switches. Yes. What do you mean? Correct. Correct. Okay, so that's what we're going to look at. So now what you're going to do is, now you have to set the input common mode. So the assumption is, you can't do anything about the circuit coming in, right? So you're already assuming that the circuit coming in is differential. You're trying to reduce the offsets introduced by your circuit, right? You can't do anything. I mean, there are other techniques which you can do to, remove the input common mode offsets. That's a whole different issue, right? Here you're just trying to tackle the offset introduced by the amplifier alone, right? Yeah. You're assuming. See, the idea is, if your input is differential, if you take a real amplifier, because of offset output, has a dependence on, you get these cross terms, right? So because of that, you won't get ideal common mode to be 0 and so on, right? That is the case. That is the case which you're trying to solve, right? The question about what happens when input is, has different common modes between the two differential cases, that's a whole different issue, okay? So you'll need this. This is A, these are A and B. Oh, okay. Okay. So now what this means is, so now you have a clock going into S3, S4, S5, S6, which are going to establish your common modes. Oh, sorry. This needs to be clock bar. S1 and S2 need to be driven by clock bar. Okay. So that when you are trying to sample your offset onto these capacitors, you're going to open these switches, right? You're going to establish some input common mode here, output common mode there. Okay. This will be the overall circuit. So this thing is called, actually this technique is called output offset storage, because you're basically taking your offset, storing it on some output capacitors. Okay. So now what happens is, this thing is fine if you have, let's say, amplifiers with, low gains. Okay. Typically, if you have amplifiers with high gains, what happens? So you have some. Okay. So remember that the input referred offset is a fictitious quantity. It's like input referred noise, right? All the offset actually, exists at the output. If you have high gain, so in other words, so let's say you take a differential amplifier, you have, large high current and high resistance. output offset voltage is going to be larger also. That's a fact. Okay, because let us take the case where there's just resistor offset, right? Your output, right, offset is going to be your current times delta R, right? If you want larger gain, which means larger current, you will have larger delta R. Similarly, larger resistors means larger delta R. Okay. So in other words, what happens is, if you try to have this kind of case, this amplifier can actually be pushed into, so if you have a large offset at the output, so remember what is the characteristic of an amplifier. So let's say, okay, something like this, let's say. So ideally you want to be operating here, okay, but this offset could push you somewhere, okay, where it could saturate the output is what I mean. Okay, so your offset could be, output offset could be large enough where it could take you into the nonlinear region of the amplifier, okay, which you don't want. Okay, so now that means it may be better to look for a different technique. So the other technique is called input offset storage. So that means obviously we need capacitors at the input. Okay, so this technique is called input offset storage. So let's see what happens when, let's call these, name these switches S1, S2, S5 and S6. So now S1, S2 are open and S3, S4, S5, S6 are closed during your offset measurement stage, offset measurement phase. Okay. Okay, so let's, oops, sorry, this is obviously wrong. C1 and C2. Again, these are X and Y. Okay. What happens during this case? So you're basically placing the amplifier and unity gain feedback. Okay. So in other words, V out directly appears across VXY. Okay. Okay. So that means you can say V out is minus AV times, originally it would have been VXY minus VOS, but this thing is VXY is V out, so it's V out minus VOS. Okay. So now your V out is approximately equal to VOS. And this is also VXY. So in other words, now you're going to take your offset voltage and store it on C1 and C2. instead of at the output. Okay. Okay. So now this is better, but now we have we want to tackle one more issue, which is adding these series capacitors. So remember, I think did we talk about this? The fact that capacitors always come with their own parasitics. So if you take any IC capacitor, you'll have parasitic capacitance to ground from here, parasitic capacitance to ground from here. Okay, and typically the bottom plate will have larger capacitance. So if you have a capacitor like this, the bottom plate is closer to the substrate, so it has larger capacitance. Okay, so if you have the signal coming in here, you're degrading because you're losing some of the signal to ground. Okay, so now you want to get rid of these capacitors in the signal path. Okay, so that's what you want to do. So the way to do that is, what we are going to do is we are going to use an auxiliary amplifier, so a second amplifier, and that is going to have capacitors where we are going to store this offset. Yes. Those capacitors will be compensation, offset cancellation. Okay, I mean offset measurement. In this case, you're doing offset measurement. So, yes, when you apply, so what is going to happen? So Vxy is right now V offset, right? So that offset voltage is stored across these capacitors as a DC voltage. Okay, so that in the next case, you're going to open this, apply the input here. Okay, so the actual input you're going to get is going to be input V in signal, right, plus VOS, okay, and then you're going to get a minus VOS, so that you apply V in directly across this amplifier. Okay, that is the idea. You store this VOS across the capacitor, you are basically storing it and adding it to the input, and then it gets subtracted from this, and only the input voltage gets applied at the input of this ideal amplifier. Okay. Okay, I'm going to see, even this will also require, I'm going to get rid of some, it may be easier to, okay, so I'm going to assume that the input common mode is established, okay, it makes it faster to draw it. Oh, sorry. Okay, so now I'm going to have a second transconductor, which is GM2. So now what I've done is I've split the amplifier as a GM stage and a resistance stage, and I'm going to add another transconductor stage. Okay, the reason I've shown it with transconductors is because to cancel the offset, we want to add, we actually want to subtract the signals here at these two nodes. Okay, if you use voltage amplifiers, it becomes a lot more difficult to subtract. Current addition and subtraction is very easy, right? So, you know, it's much easier to use transconductance stages. That is all. Now remember, this one has its own offset also. Okay, so okay, and of course the R is just a transimpedance stage, right? You're applying a current at the input, you get a voltage at the output. Okay, so maybe I'll show this anyways now that I'm done. Okay, so during the first phase, you're going to open S1, S2 and close S3 to S6. Yes. Yes. Yeah. I'm going there. Yeah. Sorry, there is one more. You need the capacitors. Yes. In this case. Oh, even the previous case. Okay, so the idea is, what you're doing is you're storing this large DC voltage across. See, what you're storing at the output is AV times VOS, right? So you're basically storing a large DC voltage across this. So see, what happens is when your gain is very large, your output DC offset is also going to be very large, right? So which is why you don't want to shift the amplifier into its nonlinear region. Okay, so for example, one thing which could happen is if you don't. Okay, so what you have to do is during this phase when this is closed, the DC will take some time to settle. If you're not careful, if you open these switches before the DC settles, your offset voltage which is stored on this capacitor will be different from the real offset. Okay, in which case that mismatch could cause problems if it's large enough. Okay. How do you separate the VCM? No, the idea is it is not about this. So what you want to do is make sure the amplifier is in the same operating point when you are trying to measure the offset. That's all. The actual, see, in normal operating condition, you don't need these two, right? The common mode is, you assume it's either established inside or it's typically established from the previous stage. Similarly, this thing could be established in the common mode for the next stage, right? You want to make sure it's in the same condition when you're measuring the offset. That's the reason why you want to use these two. So everybody got this figure? Okay. So now again, for this circuit, we can write, KVL, KCL and try to find out, right? Just like we did previous case, we can try to find out what the overall output voltage is as a function of the offsets and the GMs and Rs. This is the current coming out from GM1. Okay, GM1 times VOS1 minus GM2 times Vout minus VOS2. So Vout minus VOS2. Okay, whole thing times R is again Vout. Okay. So now you can express Vout as GM1 R VOS1 plus GM2 R VOS2 over 1 plus GM2R. Okay, so this is the voltage which is stored on C1 and C2. Okay, now that we have found out Vout, we want to find out the overall input referred offset of this combination. Let me see if I have left out something. Yeah. Okay. Now the overall input referred offset is going to be V out over. So in normal operating condition, you know that this is going to be open, this is going to be open, and this is going to be closed. And that is when you are interested in the overall input referred offset, right? So now you are going to take the overall offset you have discovered divided by GM1R to find out VOS total for this overall combination. Okay. So now you can say if GM2R is much greater than 1, you can actually simplify this. Okay. And you'll find that you'll get two terms. So VOS1 over GM2R plus VOS2 over GM1R. Okay. So this, very obviously reduces, depending on your gain which you have in your circuit, this will reduce your overall input referred offset. Okay. Now so now what you're doing is, you're basically turning on and turning off these switches at a certain frequency. Okay, so you're sampling, the offset onto these capacitors and then removing it and letting your circuit operate. So there will be some delta T time difference between these 2 points. Okay. What you can show is, at approximately, at frequencies below 1 over delta T, you can show that this kind of thing, what would you expect when you're doing, let's say this is very slow, right? What would you expect? You, along with your offset, you'll also be sampling the noise of your circuit. Correct? And if you consider slowly varying noise, which means low frequency noise, that will also get sampled and cancelled. So let us say every time you want to amplify the input, you sample the offset, go back to amplification mode, sample the offset, go back to amplification mode. If you keep doing this as a cycle, right? So every sampling instant, you'll be capturing the noise plus offset, and you will cancel noise also for low frequencies. You can't cancel high frequency noise, but this one will also, you can show that it also cancels low frequency noise. Okay. So now that's it for mismatches. Do you have any questions before we move on? The main idea is, if you see, these capacitors C1 and C2 are no longer in the signal path. So now your signal path is pretty much the same, except for these switches. They're pretty much the same, right? You don't add these capacitors, you don't add capacitive parasitics mainly. That is the advantage of this one. Okay. It could actually be quite simple. For example, you know that if you take just an op amp, right? Let's say take a single stage op amp. Your GM1 is just a differential path. Your R could be a resistor, could be a PMOS current mirror load, could be right? But that stage is there, and you can add a current as a separate differential amplifier, right? It's not that difficult to implement something like this, a simple version of this. No, actually not at all. If you see, that's why we took VOS1 and VOS2, right? The two offsets are not the same. They are two totally different offsets, right? We took the effect of both into account, right? So if you see, the first transistor, right, first transistor amplifies GM1 times VOS1. The second one amplifies GM2 times VOut minus VOS2. So we don't assume anything about these offsets. But it so happens that the offset of the first one goes down as the gain of the second one, the offset of the second one goes down as the gain of the first one. That's all. Okay. Actually, maybe we can stop here, but I do have a question. Did you cover poles, zeros, frequency responses of circuits in the previous class? I think you did. I looked at your notes. It looks like you did. Is everybody clear on that? I don't want to concentrate too much time on this because we need to go on to feedback. But I wanted to find out, is everybody comfortable with that? Okay, give me some feedback now, right? Yeah. Basics, okay. So what do you mean by basics? That is the question. So what did you learn? So why don't one or more of you tell me what you learned last semester? Analyze first order systems. I thought you looked at second order systems also, with damping and so on, and ringing and so on, right? So depending on the damping factor, you can have ringing or, right, settling. You studied Miller compensation. Sorry? That's the last topic, right? Now, do you know, for example, did you study Bode plots? You must have studied either in this course or a different course. So what happens when you have poles and zeros in the system? Can you plot the Bode plot? Right? That knowledge is pretty straightforward, right? If you have, did you study gain margin, phase margin? You have studied that. Not gain margin, but phase margin you have studied. Okay, if you know phase margin, gain margin is pretty straightforward, right? What is there, so what's so special about it? Okay, so obviously phase margin is, what is phase margin? When your gain goes to 0, you're trying to find out how far you are from 180 degree excess phase, correct? Similarly, you can say when you go to 180 degree excess phase, how far you are away from 0 dB gain. That is your gain margin. Okay, it's not like rocket science, right? It is pretty much the same. Okay, so that is good. So in which case, I will assume you know about basic poles and zeros. We'll study feedback some more. I think you have studied basics of feedback, right? So we'll study it in a little bit more detail for maybe a week or something, and then move on to more complex, maybe the op amps, right? More complex op amps and different ways of compensating op amps. Okay, so if you are not sure about any of these basics, better read up your notes again from the previous semester. Okay.